Hi, welcome back to the 1108 Labs, and by now we've worked our way up near the end of the course. We're going to start talking about circuits. Circuits are going to take the next two labs as we do various things with them. The circuit lab is kind of different from the physics we've been talking about here. The big difference with circuits is up until now we've been talking about things moving kind of as if they were little balls flying through space and they didn't run into each other or interfere with anything else. Circuits are where things start moving in a totally different way, and the way they move is kind of like a river flowing along through its channel. And if you keep that picture in mind, circuits get a lot easier. Circuits are basically about three new ideas, and these three ideas are current, voltage, and then they have resistance. Current is usually known as I for reasons I don't know. And the way it works is the current is the number of electrons flowing. So if you have a big current, it means there are a lot of electrons going through a wire. If you have a little current, it means there's much fewer electrons flowing through the wire. Voltage is kind of like the pressure pushing the electrons. So if you have a large voltage between 2 points, it means there's a lot of pressure forcing electrons to go from one point to another. How many electrons actually flow is something different. That's what the current's about. So these two things, although they're related, are actually fairly distinct. And they're related by this idea of resistance. Resistance is the ratio of the voltage to the current. That is the resistance. Now, if you have a wire with some resistance in it, the more voltage you put on, the more current you get. And it says that if the resistance stays the same, then increasing the voltage is going to increase the current. If you have a different wire, it may have a different resistance. You get a different ratio. But usually you get kind of the same ratio of the two, and that is known as the resistance of the wire. This is not, by the way, a real honest-to-God physics law the way Newton's laws are. This is kind of an engineering statement. Some things, the resistance changes as you change the voltage. Other things, it's kind of a mess. But that's the basic idea. So we've got three new concepts: current, voltage, and resistance. And what we're going to be doing today is exploring how these things interact for some simple stuff. Okay, to measure these new things, we're going to have to get some new equipment out of the kit. And we're going to need the big battery, we'll need the light bulb and the little holder, we'll need the rest of the resistors. We used one resistor earlier, we're going to use the rest now. And the big new thing is this. This is a digital voltage multimeter, or DVM, and it is used to measure voltage, current, and resistance. It should be in a box in your kit. Also in the kit you will find two probes like this. To use them you have to remove the safety tips from both ends. So you just pull those out, and then we attach them to the meter. This black one goes in the bottom hole in the meter marked COM, and it shoves in like that. The red one also has safety covers. You take those off. And we're going to put that in the meter too. But there are two places for it to go. There's a red spot here and a red spot here. What's going on is these two places are used for measuring two different things. What you measure with them is written next to the plug spot. Generally, you will use the bottom one. The one on top is used for measuring large currents. The one on top is connected to a large fuse. The one below is connected to a little fuse. And you have to be careful if you're measuring a big current to use the one on top. Once you've got those plugged in, we can turn this on, which you do just by turning the dial. You turn the dial to point at what you want to measure. This part of the thing here is for measuring DC voltage. DC is direct current. That's what we want. I want to do a first thing and measure the voltage on the battery, which should be about 6 volts. So I'll put it on the 20 volt scale. The other things on here, up here you can measure AC voltage, like what's in your house. This is for measuring amperes or current. We use that side too. And over here on this part, this is about measuring resistances. And these two things at the bottom are for specialized electronics things that we will not get to in this course. Okay, so now we've got the probes plugged into the DVM. We've got it turned on to the 20 DC volt scale. We're all ready to measure the voltage of this battery. And to do that, you just take the two probes, you connect them to battery posts, and look at the number on the screen. And the number on the screen is minus 6.34. This is a new battery. It's a little bit more than what it's supposed to be. And it's negative. The number is negative because I have the black probe, that's the ground one, connected to the positive terminal on the battery. It really doesn't matter if you reverse them. And now I have the black probe connected to the negative terminal in the battery. I get a reading of positive 6.34. So reversing probes changes the sign on voltage measurements. And as long as you're aware of that, you can measure voltages just fine. Okay, that's measuring a voltage. The other thing you can do with this is measure current. And to do that, we're going to build a little circuit. We're going to take one of our flashlight bulbs, and we have here, it came on a separate card, and I've screwed it into this holder, which you should have 2 of. We gave you, I think, 4 flashlight bulbs because these things burn out when things go wrong. That's okay, don't worry about it. I'm now going to hook this up to the battery, and it should light up. So to hook it up, I'm going to take one of our wire jumpers that have these nice little clips on the end, and I'll hook one end up to the bottom part of the bulb and connect that to the negative terminal on the battery. Oh, when you use the battery, by the way, you have to unscrew these little safety caps enough to get at the metal. If you just put things on the plastic, it won't read anything. So I'll hook up a black line from negative to the bottom of the bulb, and then I'll hook up my red line. That's how I'm color coding things to keep things straight. It's always a good idea. I'll hook up my red line to the top of the bulb, and just to check things out, I'm going to just lightly touch it to the positive terminal on the battery. And the light goes on, meaning the circuit is working. I've got good connections. Don't hold it on there for long or you may burn up the bulb. And these bulbs are kind of fragile. That's why we gave you 4 of them. So doing that shows you, okay, your circuit is good. To measure the amount of amperage, the current going through this bulb, I have to do things a little complicated here, because measuring voltage you can do by just putting the probes on 2 points and it will measure the voltage between them. Measuring the current, on the other hand, means you have to route the electrons through the meter, and so you can count how many of them go by. And that means to measure current, you have to put the meter into the circuit like this. Here's our circuit. I'm going to connect this red terminal to the red probe. I'm going to put this over on 10 amps just to be safe. Put that on the 10 amp thing. Turn the DC meter over to 10 amps just for safety's sake. And now I'm going to connect the black line to my battery. So what I've got is a circuit that looks like this. Here's the battery. This is 6 volts. It has 2 outputs. Here's my meter. It connects to one of these. The other end goes over, connects to one side of the bulb. That goes back and connects to there. So I have the meter in the middle of one of these wires. That's the way it can count how many electrons go by. Now let's try just a quick contact to see if the bulb still lights up. Bulb lights means the circuit's all connected, all my connections are good. If you don't see a bulb light when you do that, it means one of your connections is no good and you should go through and check things. Now let's try it again, and this time we're going to read the meter, see how many amperes go through there, how much current. And I'm getting 0.32 amperes through my meter. If we try it again, you can see the numbers. 0.32 amperes. So what does that mean? Well, it means for this flashlight bulb, I have I equals 0.32. I have V equals 6 volts. And if I divide V by I will get R. So R is 6 divided by 0.32, and that is about 18 ohms. So there, we've now measured the resistance of a flashlight bulb when it's on. And we did it the hard way by measuring the voltage and the current and dividing those two. What do we get if we measure it using the meter? Well, we can do that too. The meter is smart enough to measure resistance. To use the meter to measure resistance, we take our circuit and move that away. Take the bulb and measure resistance. You have to put the probe back at the R input, like so. We have to flip the meter over to resistance, which is down there. This scale should measure up to 200 ohms. And then we just put a probe on one side of the bulb and a probe on the other side. And you see the bulb without it, when it's not glowing, has a resistance of about 2 ohms. It's quite a bit different from 18. Why is that? Well, it's basically because the flashlight bulb is a lousy resistor, and it doesn't follow this rule very well. And as it gets hot, the resistance in it increases by almost a factor of 10. This is why when you buy resistors, they don't sell you flashlight bulbs, they sell you something else. A precision resistor is carefully made. It is built out of things that don't do that. So the bottom line is a flashlight bulb hot has 18 ohms, and cold, it's about 2 ohms. Resistance can change with temperature. Okay, we're done with experiment 1. Let's come back and we'll start talking about using these real resistors that came with the kit. All right, now it's time for part 2 of this lab. And in part 2, we're going to worry about resistive networks. What happens if you connect 2 or more resistors together? What goes on with that? And what happens depends on how you hook them together. It turns out there are 2 basic ways to hook resistors together, and the resistance you get from the total is different for the 2 ways. So one way to hook resistors together is just to have one resistor hooked on to the end of the other resistor. This little squiggly thing means a resistor, and the lines on either end represent the wires coming out of a resistor. If you just take the wire coming out of one and hook it into the wire going into the next, this kind of connection is known as series connection. And the way it works is the resistance of the whole thing is equal to the resistance of the first one plus the resistance of the second one. So if you made a circuit that went from here to here, and you have a battery in between, you made a circuit like that, the current flowing through the whole thing would be just the same as if you had one resistor here with a resistance equal to R1 plus R2. That's called the equivalent resistance, and the idea is if you take those 2 out and put in one resistor with the equivalent resistance, it behaves the same. So for series connection, you just add them. And you can actually prove that this is a very sensible thing to happen. The other way to connect resistors is in parallel. And if you look at this diagram, you see things are a bit different here. Instead of electrons flowing through one and then through the next, electrons have a choice between going through R1 and then out, or going through R2 and then out. So this is kind of an and. They have to go through R1 and R2, and in this case, they can go through R1 or R2. And the equivalent resistance for this is quite different. The way to find it is you take 1 over the total resistance equals 1 over R1 plus 1 over R2. This may look similar, but if you plug some numbers in, you find out it isn't. If you have, say, 10 ohms for R1 and 1 ohm for R2, then a series connection gives you a total of 11 ohms. And what you get for a parallel connection is 1 over 10 plus 1 over 1. That's equal to 1.1. That's equal to 1 over R tot. And 1 over 1.1 is about 0.9 ohms. So this one you get 11, this one you get less than 1. Connecting resistors in parallel gives you very different resistances than connecting them in series. You can continue this method further. There are some rules called Kirchhoff's rules that let you analyze any network. They're in your book, or you can Google them, find out how they work. We're just going to stick to some very simple series and parallel examples. So that's the theory of what I'm about to do. Now let's hook some up and see what that looks like. In your kit, you should have several resistors. They're these things. And if you look closely on the ends, they have labels with numbers. And the numbers tell you how many ohms each resistor is. If the numbers are not clear, you can measure them with the meter. You just put a probe on either side and it will tell you. Right now it's telling me this particular resistor is 33 ohms, which is about what it says on the card. It says 32 on the cards, near enough. Anyway, what we're going to do now is make a series and parallel resistor network and measure the resistance of the whole thing. The first one we'll make is made with our two 33 ohm resistors. And to make the network, you just remove the labels. So now we have bare leads, as they're known. And to make the network, I'm going to connect these two resistors with a wire. I'll just take a wire, put the little alligator clip on one lead, and then put the other end of the wire on the other one. And right now I have a circuit from here to here made out of two 33 ohm resistors connected in series. If we go back and look at the board and figure out what the total equivalent resistance of two 33s in series is, you just add them and you get 66 ohms for the whole thing. So let's check and see what we actually have. We've got the meter set on ohms, 200 ohms. We've got the red cord in the lower spigot, the one that isn't for 10 amps. Now to measure it, I put one lead, one probe on one side of the circuit, and get off of there. One probe on the other end. So I have my two leads on either ends of these two things, and the meter shows me I have 66.2 ohms for this whole network, which is exactly what I should get. So there we go, that's good. That's a series connection. To make a parallel connection is a little bit more effort. A parallel connection means we have to connect the two at one end and then connect them again at the other end. So we need two wires. Like so. And then I will measure the resistance from one side here to the other side over here. What do I think I should get? Well, if we go back and look at the parallel connection, you see the way it works is 1 over the total equals 1 over R1 plus 1 over R2. Now you might think that's the same as that, but it's not. Algebraically, you can work out that this is quite different. And if we plug in our numbers, we see 1 over our tote equals 1 over 33 plus 1 over 33. This is 0.03, that's 0.03. Add those together, you get 0.06. Flip it over and you get 16. So what I should be seeing with the total connected in parallel is 16 ohms. Now my circuit has gotten quite messy here, but I think I got it under control. So I'll take one probe connected here, the other probe connected over there. 17.2 ohms, which is pretty close to 16. So you see, you do get a very different answer if you connect things in parallel than in series. The resistances of these two are quite different. It's actually fairly clear if you just think about it. Electrons flowing through this circuit go through both resistances. They get resistance twice, whereas electrons going through this circuit only get resistance once. So the total resistance is much less. Let's try a more complicated one where they're not the same. I'm just gonna build this, I think, and let you figure out what you expect. What I want you to do is to take a 10 ohm resistor and put it in series with a 33 ohm resistor. So here's the 10 ohm resistor. This is the same one we used a long time ago when we were heating water with it. And if I put 10 ohms in series with 33, what do you think I should get for a total? I'm not going to show you. You have to figure this one out. Okay, the other thing I want you to do is to take 10 ohms and put it in parallel with 33. So we'll hook up a parallel circuit, and you can predict and measure the resistance of the parallel circuit. You should have several different varieties of resistors in your package with which you can make different circuits. Our next lab, I think we do some complicated circuit networks, and we'll come back and talk about that. So, okay, there we go.